Hello, this lesson is about the definition of moment of inertia for area. So we're going to introduce the concept of moment of inertia to compare and distinguish between translational and rotational motion and their relation to the mass moment of inertia and area moment of inertia. Then we're going to calculate the area moment of inertia with integral method. Some students find these concepts very abstractive and difficult to understand. So by introducing the mass moment of inertia and area moment of inertia together, I hope it will help you to understand these concepts easier. Now, before start, I want you to pause for a moment and think first, what is inertia? And in what context have you already known about inertia? While inertia is the resistance of an object to change in its state of motion. So we know velocity is a vector, right? Vector has a magnitude and direction. So the change in the state of motion includes the velocity, which is the speed, how fast it goes, or the direction of the velocity, or both. Now the second question is, when you think about inertia, what physical quantity comes to mind? Well, the physical quantity you think about should be mass, right? So inertia is the resistance of an object to change in the state, and it is related to mass. Next, let's think about what causes motion. Right, we have translational motion and we have rotational motion, and we know force and moment will cause those motions, where force causes translational motion and moment causes rotational motion. So next, let's think about the relation between force and translational motion versus moment and the rotational motion. The force causes translational motion, which is also described in Newton's second law, where we have F equal to ma, the force F equals to the mass m times the linear acceleration a, or it can also be written in this way. That is, the acceleration a is caused by force F, and it equals to F divided by the mass of the object m. So now we can see mass is the resistance to translational motion, and that is why sometimes mass is called the inertia mass. Now next we know moment causes rotational motion. Can we write something similar and relate moment to the rotational motion of an object? The answer is yes. Just like the Newton's second law, we can write a similar relation between the moment and translational motion. Here is what we have. Moment about g. So we know when we calculate moment, it's about a specific point or a specific axis. So this is g, the subscript g means the axis path through the gravitational center of the body. So the moment equals to term I times the angular acceleration. So let's also write this relation in another form, just like we do with the top relation. So here, let's compare the two relations. We have on the top, we have force, which causes translational motion, and here we have the moment, which causes rotational motion. And on the other side of the equation, we have A, which is translational acceleration. And on the bottom equation, we have alpha, which is the rotational acceleration. So if mass m here is the resistance to translational motion, now here the other term I we see must be the resistance to rotational motion. So here we have G is the mass moment of inertia. So the subscript m here means is the mass moment of inertia, and is about the gravitational center, and it is the resistance to rotational motion. So for those structural designs, the resistance to rotational motion means the resistance to stress and deflection. And here the subscript m means is a moment of inertia about mass or mass moment of inertia, because we're going to also learn the error moment of inertia. So to distinguish between those two, we have the mass, the subscript m here indicate as mass moment of inertia. But oftentimes you will see this I term, the moment of inertia without the subscript. So just like your moment is always calculated about a point or about an axis, the moment of inertia is always calculated about an axis. And to be more specific, this moment mg and the error moment of inertia or mass moment of inertia in the same equation is calculated or are calculated about the same axis. So they are about the same axis, and here the g, which means is the axis passed through the gravitational center of the body. Let's take a look at how is mass moment of inertia is defined and calculated. So just like moment is calculated about an axis, the moment of inertia is always calculated about an axis. Let's pick an arbitrary axis AA here. This is the axis AA. And on this rigid body, we are gonna choose a differential element with the mass dm. Then we can find the perpendicular distance from this dm to the axis AA. Let's use r to representing this perpendicular distance. And by definition, the mass moment of inertia about this particular axis AA is the integral of the r squared, which is again the perpendicular distance from the differential mass dm to the axis AA, and it is integral throughout the entire body. And here in this equation, first we have the mass term, right? dm, the differential mass, is an absolute value, which means it doesn't depend on any axis. But the r, right? The r, the distance is related to the axis you choose, right? Depends on the axis. So after all, the mass moment of inertia is a relative term. It is different when calculated about different axes, which again means we need to specify where is the axis and what is this moment of inertia is calculated about. Where is the axis? On another note, the moment of inertia is also called the second moment, because if you take a look at this equation, right, r squared times dm, we can rewrite it as r times r dm, where the r, right, is the moment arm. So the r dm is the moment, right? The moment arm times the mass. This is the moment. And moment times the moment arm, which means, right, this is the moment of moment. So that is why it's called the second moment. Okay, this is the mass moment of inertia where we have dm in relation. How about the error moment of inertia? Let's take a look at the error moment of inertia. So just like your calculation for centroid, for centroid and then gravitational center GC and then the center of volume, then the centroid, right? We reduce the 3D shape all the way to the 2D area. So we use the same idea here. So for an object with a certain mass, if it has uniform density rho, the mass can be written as m equal to rho v here. And then we can use the volume to represent the object. And if the volume has a uniform thickness h, and then v will be equal to h times a. Now we can further reduce, right, the shape to an area. The area can be considered as a geometry reduction of the object. Similarly, if this object has a mass moment of inertia r squared dm integral over the body calculated about a specific axis, and then the area of inertia about mass can be written as rho times this can be called as the volume moment of inertia, right? And then we write v in terms of h times dA, and now we can have rho h times the integral of r squared times the differential area dA. Here we have the mass moment of inertia, which is the integral of r squared dm, and on the other side we have the area moment of inertia, which is r squared times dA. So we say mass can be reduced to a 2D geometry representation, the area, and mass moment of inertia can be reduced to a 2D geometric representation, area moment of inertia. So for the rest of this class, use the area moment of inertia instead of the mass moment of inertia. Let's take a look at this definition. Again, I sub A, which means is the area moment of inertia, or the moment of inertia of area, which is the integration of r squared. R is the perpendicular distance from the differential area dA to the axis. Again, it is calculated about a specific axis. When we choose different axes, you have a different value. And this integral term is referred to as the moment of inertia of the area of that plate about an axis. And in solid mechanics, it is used to determine the resistance of the body to internal stresses and deflection. So it is, again, the moment of inertia means the resistance of the body to change in the state of motion. And this area moment of inertia is the resistance of the body to the rotational motion or the tendency to rotation, which means it is the resistance to the internal stresses and the deflection. And also, just as we mentioned earlier, the moment of inertia is also referred to as the second moment of an error, because, right, R times dA kind of representing one kind of moment, and then moment times moment arm one more time. So this is like the moment of moment. It is called the second moment, and the unit is the length to the force power, which will be meter to the force or inch to the force power. Now let's take a look at a simple application of moment of inertia. How do we use it in solid mechanics? Here is one example. We are gonna choose the cross-sectional area of a beam. So here is the loading status. Right, we have this beam RS, and here is a constant load applied in the middle of the beam. And now we're going to consider the three different shapes. A is an I-beam, look like that. and then B is kind of a vertical rectangular cross-sectional area, and C is horizontal rectangular cross-sectional area, and they all have the same total area, and they are made of the same material. That means they have the same strength and yield strength, and elastic modulus, for example, and they will have the same mass per unit length, which means its density. And now, for the given vertical loading P on the beam shown on the right here, like that, which shape will develop less internal stress and deflection? Why? So which one are you going to choose? So your structure will develop less internal stress and deflection. So recall we just said when we introduced the error moment of inertia, it is the resistance to the internal stress and the deflection, right? So for the structure to have less internal stress and deflection, we want to have a higher error moment of inertia. So, right, the answer depends on the moment of inertia of the beam about that x-axis, the axis here, right? So it turns out that this section A has the highest moment of inertia. Because again, I recall I didn't write very well, but here is r squared times dA, right? That's the formula for calculating the moment of inertia. So for the same dA, when we choose this A, the A beam, this I beam, always have the furthest distance r from this x-axis, right? So A will has the highest moment of inertia, which means it has a high resistance to stress and deflection. So it will develop less internal stress and deflection. So many structural members like beams and columns have cross-sectional shapes like the I-beam, H-beam, or C. And why? Right? Why do they really not have solid rectangular or square or circular cross-sectional areas? What primary property of these members influences design decisions? So the answer will be the moment of inertia of the cross-sectional area, which is the primary property of these members, influences the design decisions. Again, we want to have less internal stress and deflection, and the moment of inertia is the resistance to the internal stress and deflection. So we want to have a higher area moment of inertia, so that we'll have a less internal stress and deflection developed in our structure. Okay, let's take a look at the steps that we're going to take to calculate the error moment of inertia by integration or using the integral method. Here is the example. If you have an irregular shape, the error like that, and one edge of the error or one side of the error is described by a relation between y and x. So in other words, it is written as y equal to a function of x, or x is written in the function of y. So in that case, we need to use the integral method to find the moment error of inertia. So again, based on the equation, we are going to use, so based on the equation here, again, r squared times dA, r is the perpendicular distance from the differential area A, and dA is the differential area dA. So we're going to write all the terms r in terms of x or y, and dA in terms of x and y, and integral either over x or over y, depends on the given problem. So first we're going to choose the element dA. Again, it's very similar to the calculation of the centroid, right? Choose the differential element dA. Two choices again. Either we choose a vertical strip like that shown in this figure, or choose an horizontal strip. So which one to choose? There are some guidelines that we can follow. First, we're going to choose the element that is parallel to the axis about which we are calculating for, so parallel to the axis. In this case, right, looks like we are choosing or we are calculating the moment of inertia about the y-axis, right? So because if we choose it in this way, the perpendicular distance, right, from the strip to the axis is even or is the same, is a constant value. In this case, is x, right? Is x. Again, we choose this vertical strip at a point xy, at a point xy located on this curve. We're going to choose a vertical strip all the way to the other end of your area. Now this one happens to end at x-axis, so we choose from the point on the curve all the way to the other end of the the area. So now this is the A, and this point has the coordinate of x and y, and the width of the dA is dx, right? The width of the area is dx, and because this point is x and y, so the vertical distance here is y. In other words, this strip has x, right? Dx and y. That's the dimension of the dA, right? And the distance is x. So now everything can be written in terms of x, because you have dx term, you're going to integrate over the x-axis. Now, if you're going to choose or calculate the moment about the x-axis, then probably will be easier to choose a horizontal strip. Again, that strip should be parallel to the axis. Another guideline is if y is easily expressed in terms of x, for example, equation like that, then choosing a vertical strip with a differential element dx may be easier for you to do the calculation. But this is always sometimes the trial and error. Sometimes it's about practice. The more you practice, the easier or the faster you can identify which strip is easier for you to do the calculation. And next, we can start to integral to find the moment of inertia. But of course, first, right, you want to write everything in terms of x or y. So in this case, again, we set r equal to x, right? This is the x or the r, the distance from the A to the axis, y. So we replace r with x, and then dA equals to y times dx. So here, dA equal to y times dx. So that's the kind of relation. Then we use the relation on top of here, right? The y equals to the fx. Y, we then substitute y with the equation of x. Then everything will be expressed in terms of x. Then we're going to integral over x. Let's work on together. Example, we're given this area in this figure, and we're going to calculate the moment of inertia of this area about the x and the y-axis. We're going to follow the steps. So first, let's take a look at the I of x. So we know, right, if we're going to calculate the moment about the x-axis, it's easier for us to choose a shape that is parallel to x, then the distance between the dA and the area is easier to figure out. So here is my choice of dA. And again, you want to put down probably the equation or the formula we're going to use first, right? So I of x equal to the integral of r squared times dA. And this, again, dA is chosen at a location of x, y on this curve, and is a horizontal dA all the way to the other side of the area here. And now, right, the distance of the strip dA to the x-axis is y here, right? This is the y distance because that the blue dot has the coordinate of x and y, right? And x, right? This is the x, again, the distance from the point to the y-axis, because that's the coordinate of this point, right? X and y, x and y. So now, since the overall length is 1 meter, right, this side is 1 meter, so the length of your strip here, or the horizontal length, the length along the x-axis, x direction will be 1 minus x. Right? Again, the total length will be 1, and the distance from the blue point, blue dot, to the y-axis is x, so the rest of the length will be 1 minus x. And the height or the dimension along the y-axis here, because we choose the differential strip along the y-axis, so this is the dy, the differential element has the height of dy and the width of 1 minus x, right? So here dA in terms of x and y is 1 minus x, which is the side along the x distance or along the x-axis, and dy, which is the side along the y-axis. Right now, again, we're going to integrate over the y-axis, so everything needs to be in terms of y or expressed in terms of y. And based on the given formula here, y cubed equal to x squared here on the top of this figure. We can write what x in terms of y. So x equal to y to the power of 3 over 2, right? And then leave the dy here. And we're going to substitute everything into the formula again, and now all the terms are written in terms of y. So r equal to y, so you have y squared, and then the dA is 1 minus y to the power of 3 over 2 times dy. And the integral limit along the y direction, you have from 0 to 1, so 0 to 1. And we're going to perform the integration. The answer is 0.111 meter to the power of 4. Next, we're going to calculate the I of y with Next, we're going to follow the similar steps as earlier to calculate the moment about the y-axis. And again, since we're going to calculate about the y-axis, the strip should be parallel to the y-axis. And then it's easier for us to identify the perpendicular distance from the dA to the axis y. Okay, and seems like we're going to choose a vertical strip dA at a point located on that curve, and the point has coordinates of x and y, and the width of this differential strip or the element here is d of x. Okay, we choose the CA at point x and y, and the width of this strip is dx, it's along the x-axis. And now the perpendicular distance from this dA, the strip, to the y-axis, again, since that's xy, right, this perpendicular distance is x, right, is the distance along the x-axis, and with a value of x. And the height, right, the height of this strip, the height of this strip is y. Is y here? right? And now we can plug everything to the formula for moment of inertia, right? I of y equal to here r squared times dA. Again, r squared is just x squared, right? The distance is x. R equal to x, so we have x squared here times dA. And again, dA will be given by y times dx. Y times dx, so we have y times dx replaced the dA term. Now, since we're going to integral over this x-axis because we have dx, so everything or all the terms need to be expressed in terms of x. So we have x squared, still like x squared, and we have the y, right? Y can be expressed in terms of x based on this relation given on the curve. We have x to the power of 2 over 3, and the x and the integral limit will be from 0 to 1 because that's the right range of your x-axis. 0 to 1. I'm going to perform the integration over 0 and 1 here. Then your final answer will be 0.273. And again, the units will be the length to the power of 4.